to R such that A is equal to what? Oh sorry, A dash B dash, you write like this, and there is this X dash Y dash belonging to this one, such that A equal to X dash, A dash, Y dash, and B is equal to X dash, B dash, Y dash. Correct? By definition. Now you put the value of A here and put the value of B here. So C is equal to what? C is equal to X dash, A dash, Y dash into Y, and D is equal to what? D is equal to what? X by means X dash, B dash, Y dash into Y. That is XX dash into A dash into Y dash Y, and this is equal to XS dash into B dash into Y dash Y. Now you see X dash, X is from S1, X dash is from S1, so X dash from also S1, Y dash is also from S1. So situation is here that you see XS dash comma YY dash is from S1, and A comma A dash comma B dash belongs to here from R. Correct? So now C comma D will belongs to, of course, see XS dash Y dash is from S1 and A dash B dash from R. So of course C comma D will belongs to where? RC, belongs to RC. It implies that we have taken an element from RCC and we have shown it is an RCC. So RCC is contained in RC. So it's hence RC is equal to RCC. So in this way we have proved. Now move to part number 3. Move to part number 3. सबमिट कर दिया कल करो. So we have to prove the third part, that is R inverse C is equal to RC inverse. Correct? So take element here. Take any C comma D belonging to R inverse C. It implies that there exists XY belonging to S1 and A comma B belonging to R converse such that XC equal to XAY and D is equal to XBY. This is the situation. Now it implies that there exists XY belonging to S1. You can just write Y comma X belonging to S1 and B comma A belongs to R such that C is equal to XAY comma XD is equal to XBY. Now you see D is equal to xby and C is equal to xay. So there exists xy comma x belongs to S1, B comma A belongs A comma B belongs to R converse. It means that B comma A belongs to R, such that D is equal to xby and C is equal to what? Xay. Correct? Now it implies that D comma C it implies that C comma D belongs to RC converse. Now can we go reverse side, that if D C comma D belongs to RC converse, of course D comma C belongs to RC. Now of course D comma C belongs to RC, then this happens. Now of course this happen, and it implies what? R inverse C is equal to RC inverse. So this part is again proved. Fourth is that R union SC is equal to RC union SC. Correct? Now one part is easy. Both parts are easy. See, R is contained in R union S. It implies what? RC is contained in R union SC. This is by part 1. Correct? S contained in R union S. It implies SC is contained in R union S. So now when RC is a subset of R union SC, SC is a subset of R union SC, it implies what? RC union SC is contained in R union SC. So it implies, so one part is over. Now conversely, take any C comma D belongs to R union SC. It implies that there exists X comma Y belonging to S1, A comma Y belongs to R, such that C is equal to what? C is equal to A comma B belongs to R union S. Such that C is equal to XAY and D is equal to XBY. Correct? By definition. Now when A comma B belongs to R union S, we can write A comma B belongs to R or A comma B belongs to C. It implies that there exists XY belonging to S1, A comma B belonging to R, such that C is equal to XAY and D is equal to XBY, or there exists XY belonging to S1, A comma B belongs to S, such that C is equal to XAY and D is equal to XBY. So it means that it implies that C comma D belongs to R complete RC, or it implies that C comma D belongs to RC or SC, isn't it? Or you can just write like this, or C comma D belongs to SC. It implies that C comma D belongs to RC union SC. So in this way, R union SC is contained in RC union SC. So this part is over. Now finally we do fifth part. The fifth part, last part, that is R equal to RC if and only if R is left compatible and right compatible. See, one part is trivial. When R is equal to RC, correct? So we have already proved that RC is what? Left and right compatible. So when RC, as we have already proved that RC is left and right compatible, then automatically R will become left and right compatible because R is equal to RC. Now you have to prove the converse side. When R is left and right compatible, then RC is equal to R. You have to check this. One part is trivial, that is R is contained in RC. You have to prove the converse part, that is RC is contained in R. Just this. So let R is left and right compatible. Then what is claim? RC is contained in R. One part is trivial because if R is equal to RC, then as we know that RC is left and right compatible, and as R is equal to RC, R also becomes left and right compatible. So we have already proved. So all of you can do by yourself. Now when we prove the converse part, that is when R is left and right compatible, we have to prove R and RC are equal. Of course, R is contained in RC, we have already seen. So we have to prove just only RC is contained in R, correct? So for this, take any C comma D belonging to RC. It implies that there exists XY belonging to S1, A comma B belonging to R, correct? Such that C is equal to XAY comma XD is equal to XBY. Now you see, when A comma B goes in R, when A comma B goes in R, implies that XAY comma XBY will always go in R, since R is left and right compatible. You can multiply from the left side or you can multiply from the right side because it is left as well as right compatible. So it implies what? When XABY, this is for every X comma Y belonging to S1, because here for every XY belonging to S, and of course S is a subset of S1, so XY from S1 it is so. Also for 1 it is also true if you do any 1 into A into 1 into B into 1, so it's true. So for all cases it is true. It implies what? Every element of RC is coming in R. It implies that C comma D belongs to R. So it implies that RC is contained in R, and we know that R is contained in RC, so R becomes equal to R. So in this way all parts are proved. Now we will do proposition 1.5.8, important proposition. Proposition 1.5.8. For every relation R on a semigroup, R hash is equal to what? Just I want to tell you what is R hash. This is what? This is the intersection of all congruences on semigroup S containing R intersection of is the smallest congruence on S containing R. It is just like RE. RE is what? Intersection of all equivalences on a semigroup. S containing R is the smallest equivalence on S containing R. One is RE. RE is used for equivalence. So basically what we have to prove, see, we have to prove what it is on the right hand side. We have to prove this is RCE. Basically we have to prove RCE is the smallest congruence on a semigroup S containing R. Means we have to prove that it is the congruence on R, it contains R, and it is the smallest congruence containing R. Then it becomes equal to R hash. We read as R sharp, basically R sharp. So let's see how we prove. We have to prove this RCE. By proposition C, by proposition 1.4.9, what we have proved. By proposition 1.4.9, RCE is the smallest equivalence relation on S containing RC. And of course, when it contains RC, it also contains R, because R is and so containing R, since R is contained in RC. So we have already proved that this relation is what? Equivalence relation. And it is also the smallest equivalence relation. And it contains R. What else we have to prove? We have to prove that it is compatible, isn't it? And after proving compatible, it will be proved that RCE is RCE. Basically, before proving this, I have to prove lemma 1.5.7. So just I pause here, and before this, I have to prove one more lemma, that is lemma 1.5.7, which I forget to tell. So lemma 1.5.7. I will prove this one. That is, let R be both left and compatible. Let R be both left and right compatible relation. Compatible relation